In the 19th lecture, we will discuss the logistic regression. The generalized linear model is a generalization of the linear regression. When the error has a distribution distinctly different from normal, the linear regression may fail while the generalized linear model may work. The term should not be confused with the general linear model. The general linear model is simply several multiple linear regression models in one form as this. Here, n is the subject size and m is the number of the dependent variables. We have m dependent variables estimated simultaneously. Note that in the general linear model, instead of one coefficient estimate for each predictor, now we have a set of m coefficients for each predictor. In the generalized linear model, the outcome follows an exponential family distribution that includes common distributions such as the normal, binomial, Poisson, and the gamma distribution. The link function relates the expected value of the outcome to the predictions in the linear model. Thus, we have mu as the outcome distribution, mean, conditioned on x, and the linear regression model. The two are connected with the link function g as this. For example, the link function is the identity function for normal distribution, the negative inverse function for exponential and gamma distributions, the log function for Poisson distribution, and the logit function for Bernoulli binomial and also multinomial distribution. The logistic regression models a binary dependent variable. The distribution mean is the probability, indicating the likelihood of occurrence of an event. Odds are the probability of an event occurring divided by the probability of the event not occurring. The logit function is the natural logarithm of the odds, which is eta. The logistic regression also has some key assumptions. First, the dependent variable is binary. Second, there is a linear relationship between the predictors and the logit. Third, the error term is independent. Fourth, the independent variables are not highly correlated. The logistic regression also requires larger sample size than the linear regression, especially when the event probability is low. We need at least 10 observations per independent variable among all groups of the outcome. For example, if there are 1,000 observations and the events occur at 0.5%, then we only have 5 events, and the logistic regression may not work well since there are too few events. This is an example of the logistic model. We have 30 students in 2 classes. Each class has 15 students. The outcome is a binary variable pass, which is 0 if the student failed the exam, and 1 if the student passes the exam. From the data, we have 16 students pass the exam and 14 fail the exam. We have 2 predictors. The first is the hours spent per day for the exam. and the second is the student's class. The SAS dataset is shown in the left table, and the SAS code is at the right. In the logistic procedure, we model the probability of pass equals to 1, indicated by event equal to 1. Here, we should set class as a class variable, since we should not treat class as a numeric variable. Since the outcome is logit in the logistic regression, we may interpret the coefficient as the rate of the change in the log odds as x changes. For example, students in class 2 may in average increase 0.98 in the log odds than students in class 1. This interpretation is not very intuitive. Normally, we use the more intuitive odds ratio instead. An odds ratio is the odds of the event in one group divided by the odds in another group. According to the model, the odds ratio is the exponential of the coefficient estimate. For example, the odds ratio of the predictor class is 2.66, which means the odds of pass for students in class 2 is 2.66 times the odds of pass for students in class 1, holding predictor hours constant. Similarly, we may also interpret the coefficient of the predictor hours using the odds ratio. Since the odds ratio of the predictor hour is 2.36, which means if the student spends 1 hour more per day in the exam preparation, he or she may increase 136% in the odds of pass, holding predictor class constant. Since the outcome in the logistic regression is binary, it is a type of classification method. In machine learning, classification is about predicting a label, and the regression is about predicting a quantity. Thus, the logistic regression is a classification method instead of a regression method. We may use a confusion matrix to describe the model performance for a classification problem. A confusion matrix is a special kind of contingency table learned in the first lecture. The two dimensions of a confusion matrix are actual and predicted. Using the logistic model, we may calculate the conditioned mean, which is the predicted probability of the event. Then we may need to choose a threshold value as a cutoff point. In the last passing exam example, we may simply set 50% as the probability of pass. Then, if the predicted probability of pass is larger than 50%, then we predict the student will pass. Otherwise, the student will fail. Under the threshold, we may have the confusion matrix below. 10 students predicted to pass by the model truly pass the exam. They are the true positive, since they are predicted positive and the prediction is correct. 6 students predicted to fail by the model actually pass the exam. They are the false negative, since they are predicted negative and the prediction is wrong. Similarly, 12 students predicted to fail by the model truly failed the exam. They are the true negative, since they are predicted negative and the prediction is correct. 2 students predicted to pass by the model actually failed the exam. They are the false positive, since they are predicted positive and the prediction is wrong. The table shows at the cutoff of 50%, the model predicts 12 students pass the exam and 18 students fail the exam, while actually 16 students pass the exam and 14 students fail the exam. From the confusion matrix, we may derive several important concepts. First, sensitivity or recall is the true positive rate, which is the true positive divided by the actual positive. In the example, the true positive is 10 and the actual positive is 16. Thus, sensitivity is 62.5%. Second, specificity is the true negative rate, which is true negative divided by the actual negative. In the example, the true negative is 12 and the actual negative is 14. Thus, specificity is 85.7%. Third, precision is the positive prediction rate, which is the true positive divided by the total positive prediction. In the example, the true positive is 10 and the total positive prediction is 12. Thus, the precision is 83.3%. Fourth, accuracy is the total true rate, which is the total true divided by the total number of observations. In the example, the total true is 22 and n is 30. Thus, the accuracy is 73.3%. The confusion matrix and all the related measures depend on the threshold value. In the example, we set the cutoff at 50%, and we may choose other values. If the cutoff is less than 50%, then more students will pass. The true positive will increase and the true negative will decrease. Thus, sensitivity will increase and the specificity will decrease. If the cutoff is larger than 50%, then less students will pass. Thus, sensitivity will decrease and the specificity will increase. Clearly, there is a trade-off between sensitivity and specificity. We may maximize the Uden index to optimize the threshold if sensitivity and specificity are equally important to us. Please note that we may be more interested in one aspect. Then we need to use different measures. The Uden index is sensitivity plus specificity minus 1, which in this example is 48%. The confusion matrix at the cutoff optimized at the Uden index is shown in the next slide. In the table, the values in the parentheses are the values when the cutoff is 50%. At the optimized cutoff of 65%, one student in the false positive is now predicted to be negative. The specificity increases from 86% to 93%, while sensitivity remains the same. The Uden index in this case is 55%. From the example, we know the performance of a classification method depends on the threshold value we set. If we would like to know the model performance at all thresholds, then we may draw a receiver operating characteristic ROC curve. The x-axis of the ROC curve is 1 minus specificity, which is the false positive rate, and the y-axis is sensitivity, which is the true positive rate. The graph at the right shows the ROC curve in the last example. The area under the curve, AUC, measures the entire area underneath the ROC curve. An AUC of 0.5 suggests only random effect. The Uden J is the vertical distance from the curve to the diagonal line. In the example, we have an area under the curve of 0.8, suggesting an acceptable model. The optimized Uden cutoff is marked by the red dot, and the mid cutoff point at 50% is marked by the blue dot. The graph clearly shows that the red dot has the largest Uden index. The KS statistic is another commonly used measure to evaluate the logistic regression model. The statistic is the maximum difference between the cumulative probability of events and the non-events. Higher KS statistic is indicative of a better model in practice. In summary, we discussed the logistic regression as one type of the generalized linear model. The generalized linear model is a generalization of the linear regression when the response is not normally distributed. The outcome follows an exponential family distribution, and its distribution mean is linked with the linear model through a link function G. Specifically, the logistic regression models a binary outcome with a logit link function. The logistic regression also has some key assumptions. First, the dependent variable is binary. Second, there is a linear relationship between the predictors and the logit. Third, the error term is independent. Fourth, the independent variables are not highly correlated. The logistic regression also requires a larger sample size than the linear regression, especially when the event probability is low. Normally, we may use odds ratio to interpret the results to be more intuitive. We may use the confusion matrix to measure the performance of a logistic regression model. We notice that the confusion matrix and all the related measures depend on the threshold value. There is a trade-off between sensitivity and specificity. We may maximize the Uden index to optimize the threshold if sensitivity and the specificity are equally important to us. The receiver operating characteristics ROC curve shows us the model performance at all thresholds. The x-axis of the ROC curve is 1 minus specificity, which is the false positive rate, and the y-axis is sensitivity, which is the true positive rate. The area under the curve measures the entire area underneath the ROC curve. The Ks statistic is another commonly used measure to evaluate the logistic regression model. The statistic is the maximum difference between the cumulative probability of events and non-events. A higher statistic indicates a better model.